Section 2.1 is titled The Derivative and the Tangent Line Problem. We have seen pieces of this already back in section 1.1 when we started all of this calculus business. And we've seen portions of what we're going to encounter as we move along in chapter 1 when we looked at limits. So this is sort of a combination of those things, and it takes one small step beyond that. Okay? So taking a look first, we're going to talk about secant lines versus tangent lines. This is the part where you have seen this before. So I'd like for us to first draw a graph, and you're going to draw it twice, so try to make it fairly close to the same graph each time. In fact, we'll do it that way. So the graph we're going to draw is going to look like this, roughly a cubic graph. And we're going to put 2 points on our graph, here and here. All right, so if we were to connect these 2 points with a line, all right, just a line through these 2 points. I know that's not through there, just give me a second. That's pretty close. What that line would be called is a secant line, right? A secant line takes 2 points in the curve, and it connects them with a line between them. That's a secant line. A tangent line, as we've talked about before, is this idea of it just bumping the edge of the curve, like a circle, right, back from geometry. So what we can actually do is we can create that same secant line that I had just a moment ago, like that. But what we're going to do is we're going to try and approximate this value right here as our point of tangency, the one that's right here, okay? So I'm going to take the point that's further away, and I'm just going to make it get closer to the point I care about. So what's that going to look like? Well, maybe I cut the distance sort of in half. So now here's my point. Actually, let me move it over just a little bit so my graph will look a little bit different. Okay, so let's say I use that point. So now my line of secant, my secant line looks like this. Okay, so the secant line has shifted. And then I get a little bit closer even after that. I come to over here. And I create another line. So it looks like that. My secant line shifts again. And I create yet another point, even closer. I'm not even sure if I can draw another point in here and you guys can see it. There's so much going on in my picture. And my secant line gets even closer. Eventually, if the points get close enough together, we're approximating a tangent line. We've talked about all this before, right? We did this on like the first day of class, maybe the second day of class. We kind of talked about this picture. Well, if we talk about the slope of the secant line, and I'm going to use the points a little bit differently than I've drawn in here. But if this point is C, and we were trying to get close to this point, so shifting my picture the other direction, in other words, we could call this point over here C plus H, if this distance is H part H away. And what we're letting happen is we're letting that distance that's between them become nothing, right? We want the points to be close enough together that the distance between them is virtually non-existent. So we have these points, C plus H, this point F of C plus H. And if we find the slope for that line, you know how to find slope. You take the difference in the y values and you divide it by the difference in the x values. So the two y values are F of C plus H and F of C. Okay, subtracting two y values. And the two x values are C plus H and C. And I'm subtracting the two x values. And when I subtract those two x values, of course, I get the difference between them. And on the picture, you can see, and then from the algebra, you can see that both of those give us the value h in the denominator. This is called a difference quotient. Sometimes you encounter it in a college algebra or an algebra 3, maybe even an algebra 2 class. Sometimes you don't. But there's nothing about this that's calculus so far. The calculus part is the part where we let the h value become non-existent. We let the h value approach 0. Okay? And this idea of getting the values closer and closer and closer together and letting that distance between them become virtually nothing is a limiting process. And limits are exactly what we've spent the last 2 weeks doing, right? So we're going to use those limits for this very fact. All right, so We're going to talk now about the slope of the tangent line itself. And as you look at this formula, part of it looks like the same formula that was just on the page before. This piece right here, right? That is the slope of the secant line. So what about this formula then is different if that's already the same? The limit part at the beginning. The part that says the limit as h approaches 0. That's the part that's different for a tangent line. So if we have a function and it's defined in an open interval containing c, and if the limit that we're trying to get to exists, and we're going to talk later in this lesson about when limits won't exist for these kinds of things, then the line passing through the point c, f of c, with the slope m is the tangent line to the graph of f at the point c, f of c. The slope of the tangent line to the graph of f is also called the slope of the graph. And it's going to have more names by the time we're said and done. We call it the slope of the tangent line, we call it the slope of the graph. When you look at it from a, this doesn't happen in 2.1, it may happen later in chapter 2, but I'll mention it right now here too. If you look at it more from a physics point of view, it's also sometimes referred to as the instantaneous velocity. Okay? All right, so the third way we're going to look, that was 3 already. There's one more way we're going to look at it today. But what we're going to do first is we're going to do a problem like this. Okay? We're going to do one of these limit problems. It's going to take f of c plus h, f of c, and divide by h. We're going to do some algebra to simplify some things. And this is the part that's going to feel a little bit like, hey, I think I've already done this before. Maybe I tried that when I was reviewing problems. And the answer is yes, you did. Okay? So the example we're going to take a look at says to find the slope of the tangent line to the graph of the function, and it says at the given point. It gives us a specific point. So I'm going to do this problem with the given point in consideration. Okay? This is not my favorite way to do the problem. I'll show you another way to do another problem without any points given, and you can always do it that way too if you like it better. So we're going to do it the way that they've designed the problem to be thought about. So what are we supposed to be doing? Well, we're supposed to be finding this thing. Okay, so we're going to write that definition out on this other page. We want to find the limit as h approaches 0. My function's g, so I'll call it g of, and the c value is the number 1. So this is g of 1 plus h minus g of 1 over h. Okay, so we changed f's to g's because my function's called g. If you call it f, I'm not going to freak out on you. It's going to be okay, all right? So if you call it f, we're good. We are going to replace the c with the 1 because that's our x value. Okay? This is when you get to put your algebra hat on. What in the world does g of 1 plus h mean? Well, some of you are like, I know what it means. Why are you asking such a weird question? And others of you are like, I don't want her to call on me because I'm not exactly sure what she wants me to do. So we're going to start with an easier question so that everybody's on the same level playing field. What in the world would g of 1 mean? How would I find this? I would plug in 1 for x, right? Everybody's good with that, right? Plug in 1 for x. So let's do it. What happens if I plug in the number 1 here in this equation for x? What do I get? 5. So the very end of this is going to say minus 5. So the notation g of 1 means plug in 1 for x. So what would the notation g of 1 plus h mean? Plug in 1 plus h for x. So I can't do that quite as cleanly because part of that's a variable. 1 plus h gets replaced, or is replacing the x. So this is what we have. Okay, is everybody okay so far? Now, until we actually plug in 0 for h, we're going to write limit on every single step, right? Yeah. So that's the first place we start on our next step. Now, 1 plus h is not 1 squared plus h squared. Don't get yourself all twisted up into thinking there's a distribution there going on. You can't do that. What 1 plus h squared means is 1 plus h times 1 plus h. Okay? So this piece, oops, I didn't mean to do that. This piece right here means 1 plus h times 1 plus h. So we're going to have to FOIL, right? First, outer, inner, last, distribute. So I'm going to leave it in parentheses for now. We'll distribute the negative through in a minute. But what do we get when we have 1 plus h times 1 plus h? 1 and 2h and what else? H squared. Don't forget that minus 5 on the end. It doesn't go away yet. Okay, everybody good? Nice. Okay. We're next going to distribute the negative. So I have 6 minus 1 minus 2h minus h squared minus 5, a lot of negatives in this problem, over h. So somebody tell me what you see happen next. Combine like terms. And on the numerator, what's going to happen on that? Right. All of this adds to 0, right? And that will always happen on these. The part that's at the end, the minus whatever you have at the very end, will be eliminated with something from the beginning. Always. So if that doesn't happen, go back and look for your mistake. You have made one. Okay? It will be in there somewhere. You'll be able to find it if you know what you're looking for. All right, so these are going to add to 0. The cool thing is, again, this will always happen too, everything in the numerator now has what in it? An h. It has to, otherwise it's not going to cancel with the denominator, and we have to have it cancel with the denominator. We can't plug 0 in. Okay? So we're going to factor that h out of the numerator. That's going to give me negative 2 and minus h over h, because then I'm able to do the cancellation in the denominator. I will take one more step of rewriting just to make everything very clear for us. I now have negative 2 minus h. Limit as h approaches 0 of negative 2 minus h. And if I plug in h equals 0, what do I get? Negative 2. So the slope of the tangent line to the graph of g of x equals 6 minus x squared at the point 1, 5 is negative 2. Okay? All right, so here is the last of my list of 4 names for what this thing is called. Can somebody tell me what I called it before? What are the things I've called it so far?
Slope of the tangent line.
Slope of the tangent line. Somebody else. What was it? Slope of the graph.
Instantaneous velocity.
Instantaneous velocity. Some of you are like, yeah, physics. There we go. Instantaneous velocity. And then the last one is going to be the derivative. Ah. And you know what? When we come back next Monday, you know what we're going to do? Simple derivative rules, but not today. Today we're using the limit definition for derivatives, okay? Which is really good because it's more practice for your test on Wednesday, right? Absolutely. All right, the derivative of f at x has several notations. The one that we're introducing first and foremost is f prime of x. And do you recognize the limit as h approaches 0 of f of x plus h minus f of x over h? Does that look at all familiar? I hope so. It's like 2 slides ahead. It's right above, on the sheet of paper you had before. It's the same thing we had before, except what? What's different? I've got the f prime notation. There's one other thing that's different. X is in it, right? The definition I had before had a c in it, and this one actually has x in it, so why does it matter? Well, the first definition was the slope at a specific point, c, f of c. This definition says we can do that kind of like anywhere as long as the x value is defined and has a limit value at it. It's more general. We can leave the variable as x. So it says provided the limit exists, and then for all which this limit exists, f prime is a function of x. For all the values we can use, that's what's missing. For all x, there's an x supposed to be in there. For all x for which this limit exists, f prime is a function of x. Okay, so we're going to do another problem. But what is different looking about this problem compared to number 1? Doesn't give us a point, right? There is no 1, 5 like there was in the first problem. So we can't plug in a number 1. I mean, there isn't a number to plug in. We're going to do it in general. However, the process starts out very similarly. So it says the limit as h approaches 0. And we're going to generalize it by saying f of x plus h, our function's name is f here, so we'll leave it as f, minus f of x over h. Okay, at the beginning, I'm going to write that we're finding f prime of x. That's the notation for what we're actually finding in this problem. All right, so just like on the last one, we're going to keep writing limit as h approaches 0 until we plug in 0 for h. And we can't plug 0 for h at the beginning because that would give me 0 over 0. Right? So what we're actually looking to do is to remove a discontinuity, aren't we? It's that 0 over 0 stuff that happened back in chapter 1. Okay? So what is f of x? What is the end of this going to mean I do? Yeah, I put in the exact equation I was given, right? It's the 1 over x squared. I still have my h in the denominator. So the nice thing about this notation is the ending of it is what you're given. You don't have to find anything. It's just what you're given. What will f of x plus h be?
1 over x squared plus h.
Close. X plus h and then squared. Yeah. That's not so friendly. Okay, so I don't remember who it was on this board on the side last time, but you guys were doing this one, or a very similar problem to this. Who was working on this board last time? You guys were. Weren't you doing a problem that had the double fractions going on? Yeah. Okay, so when we have a fraction inside of a fraction and we're trying to simplify, I haven't done one of these in class. What do you have to do in order to get this to simplify? Yeah, we need a common denominator. Our goal needs to be to get rid of that double fraction. And the only chance we have at doing that is to get a common denominator and try simplifying some stuff. Okay? So before we can get a common denominator, I need to figure out what that first denominator is when it's written out. So what will that first denominator be when it's written out? Like so. I still have minus 1 over x squared. This is all over h. All right, common denominator, what's it going to have to be? Just the two things multiplied, right? I mean, it's going to be a mess, I agree, but it's going to be those two things multiplied. So if I multiply this first fraction by x squared over x squared, and I multiply the second fraction by x squared plus 2xh plus h squared, then the first numerator is just x squared. The second numerator is exactly what I've already written down, but negative through all of it, right? So minus an x squared, minus a 2xh, and minus an h squared. And I'm going to leave the denominator as the two pieces multiplied and not actually, simplify to multiply them out. And this is supposed to be all over h. Okay, so let's deal with the numerator first. What do you notice in the numerator? Yes, the x squared and the negative x squared cancel, right? That's good. Everything in the numerator now has an h in it. I mentioned that before. We're going to need that to happen. I'm also noticing that this feels a little bit awkward now to have all of this over h, right? So what we're going to do is we're going to, instead of dividing by h, what can you do instead of dividing by something? Yeah, you can multiply by the reciprocal. So we're going to multiply by the reciprocal of h, which would be 1 over h. You guys remember that? And that's why I needed those h's in that numerator now, is because that h that I just now am going to have right here, this h, it's going to cancel with those h's in the numerator. So bear with me a second. Let me rewrite this. So you have the limit as h goes to 0. The numerator, like we said, the entire piece of it, each part of it has an h in it, so we're going to factor the h out. I'm going to be left with negative 2x minus h. My denominator has x squared plus 2xh plus h squared times x squared and times h. And then the h's will reduce. That step of reducing or canceling those h's is exactly what allows me to now go ahead and plug in a value of 0 for h. Let me rewrite one more time what we have just to clean it up just a little bit. If you don't want to do this rewriting step, that's totally cool. I have negative 2x minus h over x squared plus 2xh plus h squared times x squared. And now we actually have the ability to plug in 0 for all my h's. So what's my numerator going to give me? Negative 2x. What's my denominator going to give me? X squared times x squared, right? What's x? Because this piece right here is going to be left, and this piece is going to be left. Everything else is going to 0 out. So what's x squared times x squared? X to the 4th. Can we simplify one more time, maybe? Yeah. And this will give me negative 2 over x cubed. And this is the derivative of our function. Now, you probably should be a little concerned, because just a minute ago we just said that we could call this the slope of a tangent line. And this does not look like the slope of anything. It's an equation. So how in the world would this give me the slope of a tangent line? Well, let's say, for instance, we had done this problem over here, and we'd left the x in it all the way to the end. Okay? We didn't plug in x equal 1 like we did at the beginning. We did it just like we did the problem right now, number 2, but with x all the way in it to the end. What it means is that at the very end, I could plug in the 1 for x instead. So the nice thing about this formula is that this formula can find the slope of the tangent line on the entire graph. Now, I don't have to redo it for x equal 1 and x equal 2 and x equal 10. I could actually put the 1, 2, and 10 in at the end here and find as many slopes as I wanted to very quickly. Okay? So that's the relationship. All right, we're going to do another one. We're going to go a little bit further into this process. And we have a radical because I've done some fun ones for you today. I thought a radical was due. All right, so find an equation of the tangent line to the graph of f at the given point. Okay, so that's not exactly the directions we've had before, right? It says to find an equation of a tangent line. So let's just jot down what you remember in terms of an equation of a line. What in the world would an equation of a line look like? There are a couple varieties. So somebody tell me what you remember as an equation of a line. Very good. Any others that you remember? Did you remember one, Caleb? No? Well, it's an equation of a line. I want a general equation of a line, though. There's another one that I'm thinking of that would be a little more helpful in this problem. The reason this is the formula that's a little more helpful for this one, not because we couldn't use the other one, but the reason is because they give us the point of an x and a y. So those values they give us right there are going to be x1 and y1. That's why it's a little friendlier to use this. So if you take a look at this one, I already know that this is 1 and this is 1. X and Y themselves are part of the line's equation. The only thing I really don't know is M, right? M is a slope. And that's what we've been doing, right, is finding slopes, aka derivatives. So we're going to find the derivative of this guy, and that's going to be our slope when we plug in x equal 1. Okay? So first things first, we're going to find the derivative. So we're going to find f prime of x. So this is the limit as h approaches 0 of f of x plus h. I'm sorry, I wrote that wrong. Here we go. F of x plus h minus f of x over h. Could you find f of 1 plus h minus f of 1 over h for the problem? Sure. If you wanted to put the 1 in place of the x and do the problem with the 1 in there, you're okay to do that. Somewhere along the way, you're going to plug in 1 for h. It doesn't matter really where, okay? So I choose usually to plug it in at the very end. All right, so then, what in the world would f of x plus h be? Square root of x plus h minus f of x. Well, that's the problem they gave me, right? It's the square root of x over h. This kind of looks like the quiz question I gave you, wasn't it? A little bit. Not identical, but it's a little bit like that one. We've got radicals involved. Can't cancel that h out in the denominator if we can't get the h out from underneath the radical. So we get the h out from underneath the radical by rationalizing, right? And we do that with the conjugate. So what is the conjugate of that numerator?
Square root of x plus h
Mm-hmm.
plus square root of x.
Fabulous. Is everybody good with that? And of course we do that on the top and the bottom. In the numerator we want to multiply that out, in the denominator not so much. So when we multiply that out in the numerator, because it's the conjugate, it reduces all those radicals. The inner and the outer terms, like foiling, are going to be 0 when added together. And I'm going to get x plus h from the first one minus the x from the second one. First terms multiplied give me, first times first gives me x plus h, last times last gives me square root of x, or gives me the x from the square root of x. And then the denominator stays in factored form because we don't want to do any more work than we have to. And if we do distribute that out, it starts to look funny and you probably can't see it as easily what you're supposed to do. So what happens in that numerator right now? The x's add to 0. So everything in the numerator, not that there's much, but everything in the numerator has an h in it, right? So what happens with the h in the numerator and the h in the denominator? They reduce to 1, right? They divide out to 1, or they cancel. Make sure that you're realizing then they cancel to a 1 in the numerator. So this leaves me with the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. So that looks pretty good because now I can plug in 0 for h. So if I plug in 0 for h, what do I get? Square root of x plus the square root of x, which would be what? 2 square roots of x, exactly. We found the derivative. That was not what we were supposed to find. I mean, we needed to find it, but we're not done. What are we supposed to do with this derivative? This is f prime of x. We're supposed to plug in 1. All right, so let's come back up here. The m value I'm looking for is this derivative with the number 1 plugged in. So when I take 1 over 2 square root of x and I plug in 1, what do I get? 1/2. And in my equation then up here, I can plug in a 1/2 right here. All right, so we're going to find this equation now. I'm going to go to a different slide. I forgot to leave a blank one in here, so let me go to the end here. So now you've got y minus 1 equals 1/2 times x minus 1. And we'll simplify. Y minus 1 equals 1/2 x minus 1/2. And we'll add our 1s. This is y equals 1/2 x. And if I add a 1 to a negative 1/2, I'm going to get a positive 1/2. So what I'd like for you to do real quick is grab your calculator. I would like for you to put the original equation in your calculator, which was y equals the square root of x. So put that in. One of them is y1, the other one is y2. Because this is the second part of these directions. This direction said, use a graphing utility to graph the function and its tangent line at the point. Okay, so what does that mean? Well, you're going to have a graph that looks something like that for x square root of x. And you're at the point 1, 1 right here. And your grapher, your calculator, should draw this in such a way. I didn't draw mine very well. It's probably going to draw it better. Oh, that's not too bad. I've got mine colored, but this is the picture you should be seeing, or something very close to it. You might need to zoom in or zoom out, depending on what your window is, to see that this is the equations, the graphs of the equations you have. Okay, so this is part B of the problem, is to graph this, to draw this picture. Is everybody's calculator showing them an image that looks something akin to this? Is it looking like that? Fantastic. All right, we have just a couple more things to cover real quick. There are 3 locations where tangent lines do not exist. The first one is at discontinuities. So what do discontinuities look like? Well, we've talked about them a lot. They're things like holes, jumps, asymptotes. And it should make sense to us that the limits don't exist, because if you've got a hole, you have the limit value there, but you don't have the function value there. And in order to have this work, we have to have both. If you have a jump in the graph, the limits from the 2 sides wouldn't necessarily be the same thing. And obviously, if you have an asymptote, you've got the worst case scenario, because it's almost like the limit values are completely far apart, typically speaking, or they're approaching infinity or negative infinity, possibly even both infinity. Sharp turns is the next one. So you might have an image that looks like this. The problem with this is at this point right here, if you look at the limit from the right and the limit from the left, they're different. In fact, one of them is negative and one of them is positive, right? Those slopes, the slope from the left-hand side is looking like lines like this. Wow, that wasn't good. And the slopes from the right-hand side look like that. Right? Slopes from the left are negative, slopes from the right are positive. Not cool. Not cool. Vertical tangent line, this is one that we always throw in here because it legitimately exists, but you're probably never going to run into it. Okay? So if you had a graph that had a strong enough vertical component right here, so that you actually created a vertical tangent line like this, this one would be said to have no derivative, because the slope of a vertical line is undefined. So the derivative would be undefined. It has a tangent line. It'd be like x equals 5, or whatever, but the derivative doesn't exist because the slope does not exist. All right, we have just a couple more examples left. Not example, one definition then an example. Differentiability. If you know that a function is differentiable, that means it has a derivative, it is automatically continuous at that location. And what I want to say for sure for you to understand is that the reverse is not true. Just because something is continuous does not necessarily mean you have a derivative. And that sharp turn example is a primary case of one that happens. Continuous, no problem. Did not pick up my pencil whatsoever when I drew that, right? But that sharp turn point at the bottom does not have a derivative. Okay? So you might be thinking about graphs of, say, absolute values. It's a classic example where you see that happen. And that's exactly what our example is going to be on the next slide. Okay? Take your calculator, and I'd like for you to graph this. It's an absolute value function, but it's not the same picture as the one I drew before. So I'd like for you to take your calculator, graph it, and I'm going to sketch a graph up here as well of roughly what it looks like. It's such a fun picture, isn't it? I bet you didn't even know your calculator could do that. Does everybody know where the absolute value feature in their calculator is? Okay, if you don't, just check with me after class and I can find it for you, okay? This has places where the derivative doesn't exist, and that's exactly what this question says. It says to describe the x values at which f is differentiable. So it's kind of like with continuity. We look for the places where it isn't, and then we describe it the other way. So where is this not differentiable? Well, here and here. And if you can see it closely enough in your calculator, you can figure out what those values are. And I'll tell you it from an equation standpoint in just a second. Can you tell me what those values are if you did get it graphed? It's -3 and 3. And the way you can think about it from your equation standpoint is exactly where this equation would equal 0, because that's where you're hitting the x-axis. So if I plugged in 3, I would get 0. If I plug in -3, I get 0. So the question, though, asked us, where is it differentiable, not where is it not differentiable. So be very careful you answer the question that's asked. Well, it's differentiable from -infinity to -3. Those are parentheses on the end. They mean I'm not allowed to equal them because infinity is not a number anyway. -3 has this issue. You do a union symbol. You go from -3 to 3. All those values in between them are good. Another union symbol. And then 3 to infinity.
They're all parentheses.
They are all parentheses. The only other option would be to use brackets, like the square brackets like this one, Hudson. And those square brackets means we actually can equal a value and we can't equal 3 or -3. And infinity and negative infinity aren't numbers, so we never equal them. Yeah. Any questions on this one? So if you were doing this, I know you don't have any homework that you're turning in paper form to me for this one, but if you were doing this on paper homework, this is what I would be looking for you to show me. Your calculator's great and you've got a reference and you're looking straight at it, so just sketch the graph on there so I can see where you're getting those numbers from. Does that make sense? All right.